so on here we got 8.2 is all about Pythagorean theorem. Again, you have seen Pythagorean theorem several times. In fact, this whole chapter is all about right triangles. The first section that we did was about right triangles, with an altitude drawn in, so it made 3 similar right triangles. Now this one's about using Pythagorean theorem to solve the missing sides of right triangles, but there's a little more to Pythagorean theorem than what you've learned before. So we're going to add some stuff to that. And then the rest of this chapter is still all about right triangles. So we'll go into special right triangles and then a little bit of trig, which deals with, again, right triangles. Now, Pythagorean theorem. When we talk about Pythagorean theorem, most of you probably think about a squared plus b squared equals c squared, right? So on here, they have the equation ring. And I've written some stuff on a board over here, and I'll point to it. But there's a couple different ways that we talk about Pythagorean theorem. One of the ways that we talk about is in that format that is on the top of the paper there. A squared plus b squared equals c squared. Now, something that we actually use more often than that is actually flipping that around and saying c squared is equal to a squared plus b squared. And one of the reasons why we like to state it the other way is because of what we're going to do on the second page of this, which talks about more than just right triangles. But any way you look at it, C always represents what part of your right triangle. Not always the x side. It's the what? The longest. So in a right triangle, what's that longest side called? The hypotenuse. It's always the side that's across from the right angle. So on here, you have a diagram. And you have, this is a leg, this is a leg, the two sides are next to the right angle, right? And then you have the hypotenuse. Oh, hypotenuse, that's a U. All right, so leg, hypotenuse. Now, C is always your longest value, it's always representing your hypotenuse. So what this is saying is that the length of the hypotenuse squared is equal to the sum of the squares of the two legs. So that's that right there. Again, that only works if you have a right triangle. Now, down here they show us a couple examples, and they do Pythagorean theorem both times in order to solve for the missing sides. So here, in order to use it, first you have to recognize what part is your hypotenuse. Well, the 13, that's our hypotenuse, right? It's crossing the right angle. So since this is our hypotenuse, that's going to be our C value. So that's what we're plugging in for C. The other two, the 8 and the 12, it really doesn't matter which spot you plug them in for. Now, for these two triangles, they actually labeled the triangle as triangle ABC. So since they did that, they labeled the opposite sides accordingly with their lowercase values. But normally, they're not going to always label the triangle as ABC. So it's going to be whatever parts they give you. And a lot of times they'll have your X or whatever you're starting for, not in the hypotenuse position. They might have for one of the legs. Could be the hypotenuse, but they're going to mix it up. So on this one, we have the hypotenuse that went in for C, the 12 in for B, and then we're solving for A. As you ran through the problem, again, you had to square the different parts. So 12 squared gave us 144, 13 squared gave us the 169. Subtract, you're left with a squared. How do you get rid of the square? You have to square root in order to get rid of the square, and we're left with 5. Gave us a nice whole number. Now, for B, very similar, but this time the missing value was our hypotenuse, which was labeled as C. So C was actually our C value we plugged in. The other two values, the 20 and the 30 range for A and B, since those were our legs, and we solved. Now, Pythagorean theorem is a little bit easier to use when we're solving for the hypotenuse, but again, it's not always what we're going to be solving for. So we squared the two numbers, we added them together, took the square root, and we got our answer. Now, this time, the answer did not come out to a whole number. We got a decimal. For the majority of these problems, I would still prefer seeing exact values over a decimal answer, but again, you could get something that is either an exact value or decimal. or you could get a whole number. Now, the difference between those answers, some of these can be done a different way. Instead of using Pythagorean theorem, there is a shortcut. But again, it requires a little bit of memorization, just like the whole rest of this class does, right? Early on in the year, we were doing definitions, and we had to memorize definitions, and we had some theorems that we had to memorize, and some other problems we had to memorize. There's a lot of memorization to this class, and I know that. As we go, now there's going to be more formulas that we have to memorize. In this part, we've already seen it's going to help us to know our perfect squares for simplifying radicals. And then the next thing that we're going to talk about is Pythagorean triples. So in the first example, this is an example of a Pythagorean triple. Our three sides here were 5, 12, and 13. All right. They were all whole numbers. When you have three numbers or a right triangle that are all whole numbers for your sides, that is a Pythagorean triple. And there's certain Pythagorean triples that are going to come up all the time when we solve. So let me take this down for a second. And I want to put a Pythagorean triples. There's a lot of them. All right. Now, we need every single one of these. No, I'm not making you memorize every single one. All right. But there are two that are probably the most important. This one's definitely by far the most important. 3, 4, 5. Followed closely by 5, 12, 13. I can guarantee that in every single section from this point on to the end of the year, you'll see one of these triples on every single test that we have. You'll see them on the FSA. You'll definitely see a 3, 4, 5. I can guarantee that. And you'll see things from their families. And what I mean by that, so these are kind of the parent triples, but notice there's all these triples that are listed below them. Well, these triples that are listed below them are just those same numbers, but what? What do you mean by big? Not squared. All right, so on here, 3, 4, 5. The next one below it is 6, 8, 10. How do you get those numbers compared to 3, 4, 5? All right, so you could say that you added that same value to itself, or times by 2, right? These are the same values, just multiplied by 3. These are the same values multiplied by 4, and multiplied by 5, and so on, all the way down, right? So anytime you have a triple, you could also have another triple by taking those same numbers and multiplying by the same value. All right, on this one, 5, 12, 13, same thing. All these numbers, this is them doubled, tripled, quadrupled, and so on. Now, will these other ones come in handy? Yes. I wrote on the board over here the first 5 families that are up there on the board because these are the ones we're going to see the most often. Those top 2, probably the most important. If you can't memorize any of the other ones, you at least need to know those 2. All right, because those 2 will come up all the time, and it'll make the work a lot easier. Because instead of doing Pythagorean theorem every single time, if you recognize one of these triples, it's almost like there's no work to be done. Okay. So let's go back to the other page. All right. All right. Let's look at these examples. So on the examples, right, we have the top part. It says find x. Great. We're going to find x. But when we find x, there's a couple different ways we can do it on some of these. Now, you can always do Pythagorean theorem. So let's start the first one off. We're going to use Pythagorean theorem. We have 3 and 3 and x. Well, in order to use Pythagorean theorem, which part am I going to use as my c value? X on this one, because this is my hypotenuse down here, right? So for the first one, I plug this in. X is going to be my c value. So I have b squared or x squared. And then I have the 2 3's are my 2 What do I call those other sides? My two legs. So those are my A and B values. So I have 3 going in for one of them, the other 3 going in for the other one. So I have x squared equals 3 squared plus 3 squared. So we still have x squared. 3 squared is 9. So I have 9 plus 9, which is 18. Now, how do I get rid of the 18? So how do I get rid of the square? Square root. So square root both sides. So now x is equal to the square root of 18. Now we're back to what we did yesterday. We have another radical to simplify. What's a perfect square that goes into 18? 9. So we have, this breaks down to square root of 9 and square root of 2. What's the square root of 9? 3. So this is 3 square root 2. That'd be a good answer. All right. Now, number 2. What's x? What's the length of x? Anybody know? Just looking at this, I know right away. X is 12. Because of that. Yeah, it's one of our triples. If we look at this, 9 is 3 times 3. 15 is 5 times 3. So this is our 3, 4, 5. There 3, 4, 5, but all the values have been multiplied by 3. So the missing value up here was 3 times 4, which is 12. Now, you can use those triples to find those values. If you know them, you might be able to see them real fast and not have to do any work. All right. If you don't know them, can you go and use Pythagorean theorem every time? Yeah. So if you forget them, or if you just miss that it was one of the triples, then you'll do work. And then when we get to the end of the work, it'll be like, oh, that was a whole number. I could use a triple. But again, you can do it either way. So if I did Pythagorean theorem, let me use a different color. We have 15, that's our hypotenuse. So I could have plugged that in for my C value. 9 would win for one of the legs, and x would have been my other leg. 15 squared is 225. 9 squared is 81. Subtract 225 and 81, and you get 144. Square root of 144 is 12. Again, get the same answer. It's just more work. Let's look at the next one. Number 3. What's x? You know what x is on this one? What is the number? Huh? It is another multiple. Is it multiple? Which one is a multiple of? Let's see. What number goes into both of those? 25 and 65. 5 goes into both of those, right? This is. Wait, which one did you just say? I might have cut you off too fast. Yeah, you're right. 5, 12, 15. So 5 and 5. This was 5 and. Sorry, this is 13 times 5. So then this one is 12 times 5. So 12 times 5 is 60. Again, you don't even have to show that work. If you recognize it and you see, all right, that's just 5 times 5, that's 13 times 5. You don't actually have to show that work. You just know that that one's going to be 12 times 5, which is then 60. And that's enough. All right. That's all you have to show. Now, if you don't recognize it, again, you can fall back to our Pythagorean theorem. These numbers are huge on this problem. So now we're dealing with much bigger numbers. So I could do this in my head using the triples. It's a little bit harder to do in your head if you're not using the triples on this one. So I have x squared and I have 25 squared for my two legs. This is 4. I think this is this. You might have to check my work on that one. 25 squared, I do know that one off the top of my head. 6.5. Subtract 6.5, and that leaves us with, yeah, okay, we're good. 3,600. Square root that, and square root 3,600 is 60. We got our answer. Now again, a little bit harder to do without a calculator though. So if you recognize your triples, you do it without a calculator. Even that one that's over there, number 4, that looks like it's just massive fractions. That's still one of our triples. Well, we have the same denominator each time, but look at those numerators. I have 4, I have 5. It's our 3, 4, 5 is divided by 9. Again, could we plug in the Pythagorean theorem still? Yeah, but you don't have to. You recognize the triple. So we've seen Pythagorean theorem in at least 2 classes before you get to geometry, but there's more to it. So you have your Pythagorean triples that can help you out. There is something else that we use Pythagorean theorem for, and it's the converse, so the opposite. When we say that we're doing Pythagorean theorem, usually we say that we have a right triangle, and if it's a right triangle, then we can say that the square of the hypotenuse is equal to the sum of the squares of the 2 legs. Great. The converse, the opposite of that, if the longest side, you can't call it the hypotenuse because we don't know it's the right triangle, but if the longest side square is equal to the sum of the 2 other sides squared, then it is the right triangle. So let me get rid of this. Go to the next page there. So at the top of this one, so now looking at the converse of Pythagorean theorem. There are actually 3 things that you can do when you're doing the converse, because yes, if that formula holds true, then it is a right triangle. But if it doesn't hold true, then there are other options. All right, you see those inequality symbols there? Now, this is one thing that I feel like this book does a little bit backwards. All right, everything else I like, but if you're basing this off your C value, it makes more sense. So to list your C value first, and that's why you like writing it in this direction of C squared, because if it's a right triangle, again, C squared is equal to A squared plus B squared. If it's acute, C squared is less than A squared plus B squared. And if it's obtuse, C squared is greater than A squared plus B squared. I like writing in this order because it makes a lot more sense, because when we're talking about an acute angle, an acute angle is smaller. So comparing it with our C value is smaller, so it's acute. Our C squared value is greater, so it's obtuse. All right. Most books tend to write it the opposite way. We usually write it this way. So, but these are our 3 equations. If the C squared value is less than, it's acute. If the C squared value is equal to, it's right. And the C squared value is greater than, it's obtuse. Now, let's look at some of the examples down there. So, down here on the bottom, look at number 1. All right. Oh, you got something right away, right? This is just our 3, 4, 5. Do I actually need to show work on this one? No, because we know a 3, 4, 5 triangle is what's a triangle? A right triangle. So on this one, I can go straight for saying, hey, that's a right triangle. That's just a 3, 4, 5 times 10. All right. Now, go to the next one. All right, we got number 2, 20, 30, 40. 20, 30, 40. That one, is that a right triangle? If it is, it's not one that we recognize from our triples. All right, so we need to actually do this problem. Now, it does say at the top, first to determine whether it is or whether it can be the measures of the sides of a triangle. So that's on something earlier in the year. What has to be true in order for the sides to work as a triangle? Two small ones, all right? Yeah, so it can only make a triangle if the two smaller values sum is greater than the third side. So on here, 20 and 30 add to 50. 50 is greater than 40. So yes, this can make a triangle. So now we need to go and look further and say, all right, what type of triangle? So we're going to plug it into Pythagorean theorem. So on here, again, whoops. I don't have that. Got this set up. Okay. Those three values, which one should be the C value? 40. Why 40? It's the biggest. Yeah. So 40 squared equals 20 squared plus 30 squared. 40 squared is 40 squared is 1600. 20 squared is 400. 30 squared is 900. Add those two together. So 1600 is greater than 1300. Our C squared value is greater. Therefore, what type of triangle is this giving us? Obtuse. If C squared is greater, it's obtuse. Again, just remember, if C is equal, it's a right. If our C squared is less than, it's acute. And if C squared is greater than, it's obtuse. All right. So now go to the next one. We have 18, 24, and 30. All right. What do we want to do? All right. See if it makes a triangle. So all right, 18 and 24. Is that greater than 30? Yeah, that's a lot bigger than 30. So that one's definitely a triangle. All right. Now what? What do you want to do next? Okay, we can do that first. See if it's a triple. Is this one a triple? Yes. So they all have a common factor there. This is the same as which one of our triples? Got 3, 4, 5 again. 3, 4, 5. Just multiply by 6. So if you can recognize and spot those triples, now we don't have any work to do. We know that this is the right triangle already. Because again, all these, look, they're all whole numbers down here, right? For the most part, except for a couple. So if it's going to be a right triangle, it's going to be one of the triples. So it's a good thing to check first. All right, good eye. Let's go over to number 4. All right, number 4, we have 6, 8, 9. All right, what do we want to do first? All right, find the biggest number. All right, 9 is what? 9 is our biggest number, so 9 squared is equal to 6 squared plus 8 squared. Now, do I know that's actually equal yet? Sorry, sometimes that's taught me. Writing doesn't always work out. So 9 squared equals 6 squared plus 8 squared. Thank you. 9 squared is 81. That's 36. That's 64. If I add those together, that's 100. So they're not equal. 81 is less than 100. So if the C squared value is less than, it's acute. Now, there was something that we forgot to do on that problem. We forgot to check to see if it makes a triangle. 6, 8, if we add those together, that's 14. It's greater than 9, so we're good. It is definitely an acute triangle. All right. But now, let's say we forgot to do that stuff on the next one. We would have done a whole lot of work for nothing. Because on the next one, 6 plus 12 is what? 18. And 18 is equal to 18. It's not greater than 18. So this one, it doesn't even make a triangle. So again, make sure you always check, because if you're just to plug them in, you get an answer, but it'd be the wrong answer if it didn't make a triangle. So be careful. All right, any questions on here? So then your actual assignment, what I'm gonna have you guys do is on the next page, page 13, I'm gonna have you do 1 through 18. I think 18 problems is more than enough problems for homework. Again, some of them, you don't have to do work, you recognize those triples. If you didn't write down those initial triples that I wrote over there on the sideboard, you probably want to write down at least those first 5 on the bottom of the board over there. Any questions? All right, then have the rest of the class to work on this. I think you have about 10 minutes left, don't you? What's the? Oh, you got 14 minutes left. And you can probably get most of that assignment done in class. All right. Freeze this.